Hello, can you guys hear me? Okay. Welcome, everyone. What a wonderful day today at London. I hope you all are having a good time. I'm here to talk about how we scaled observability with Loki at Dropbox. So for next 20, 25 minutes, this is what we are going to talk about. I'll introduce the problem space, why those problems were pertinent at our scale. Then I will walk you through evaluation metric we had, using which we evaluated different logging solutions. Then why we arrived at Grafana, how we made it operational at our scale, what we have made different, what changes we made with Grafana. And finally, I'll leave some time at the end of this presentation for some Q&A. So with that, before I dive in, let me give you an intro about myself. My name is Alok Ranjan. I am the engineering manager of storage platform team. My team primarily deals with all storage services. And I worked in Loki when I was working in my previous team, in telemetry team. Prior to Dropbox, I have worked at Big Switch Networks. It was a startup, VMware, and Cisco. Primarily, my focus has been infrastructure and building scalable distributed systems. A particular interest of mine is how AI and ML infrastructure are scaling. But that is something we can talk some other time. Today, we are going to talk about how we solve logging challenges at Dropbox. To appreciate why this problem was so challenging, let's look at the scale at which we operate. To those who don't know, Dropbox is a cloud storage company. We were founded in 2007. Today, we have more than 700 million users, out of which 18 plus million users are paying users. We manage more than 1 trillion piece of content, that is user data. And we are supporting billions of files uploaded every single day. So up until 2-3 years, I'm sorry. OK. So before we delve into the problem statement, let's look at what unstructured log is. Unstructured log is the raw data, the output produced by any application. It doesn't have any schema. It's a very free-form way of printing out something. Because of this, it gives immense flexibility to application owners to dump anything and also look for things. In contrast, things like Hive or traces are structured logs where there is a predefined schema. The sources for these logs is any first-party application code, that is code we as a Dropboxer write, as well as any third-party debug files, be it any library, be it anything we have integrated in Dropbox. The primary use case of these logs are real-time troubleshooting. Prior to, I'll say, 2021, we didn't have a way of looking at these unstructured logs. All these logs were stored in var logs. Developers had to SSH into individual boxes, and they would go and do cat or tail of the log file they were interested in. One challenge here was we had a host rotation policy of 7 days. That means every 7 days, your host will get rotated out, and your logs are gone. Not only that, even within that 7 days window, if you know how logs work, logs are getting constantly compressed, right? So if you have to find something in the current log file which is being logged, it's very easy to just search in it. Otherwise, we had built a lot of tooling around it where we would just go ahead and look through different zip files. But beyond 7 days, that host is gone, entire log is gone. We were also migrating to Kubernetes around the same time. Now, these containers were even more ephemeral. There was no guarantee of even 7 days anymore. Plus, logging or SSHing into Kubernetes was not as easy as logging into host, right? So that even exacerbated the problem. So this was our problem statement. From here, we came up with a high-level requirement. We wanted to provide a user-friendly way of managing users' logs. We wanted to make it secure, so that only authorized people can access it. We wanted to completely replace our manual on-host SSHing because that was error-prone. It posed security risk as well. Third thing was we wanted to ingest entirety of Dropbox logs, like and we didn't want to bother application owners to rewrite their logs. We wanted to make it as seamless as possible because we were already going through so many different migrations that application owners were already tired of all these migrations. And we wanted to make sure whatever we do today lays the groundwork for future as well, so that whenever we acquire a company, the logs for those services are also automatically ingested. So from there, we came up with some reliability and security requirement. We wanted to have at least 1 week log storage. Again, this requirement came from the fact that there was 7-day host rotation period. We looked at different metrics to figure out what was our throughput for logs around that time. And we came up with this number, 150 terabyte per day. Today, it is way more than that. We wanted to have a ingestion latency of P99 ingestion latency of less than 30 seconds. And we wanted our queries to return within 10 seconds. We also wanted 99% of log readability and access. From day one, we wanted MTLS. We wanted to have end-to-end security. We wanted to maintain access control. Prior to Loki, this was guarded by guarding SSH access to hosts. So we wanted to have something similar, like only the authorized owner, service owner should be able to access their logs. We wanted to have some way of some key management so that logs are encrypted at rest. And we wanted to have some PII protection. Like in case of PII leak, we wanted ability of detection, filtering, and redaction. We also called out some non-goals specifically. In hindsight, this helped us a lot. And that's why I have put it here. We explicitly said we are not going to mandate any log format. That means no one has to change their logs. We wanted to call this out that this logging solution is not going to replace any of the existing tools. Like if you're relying on metrics for aggregation, keep doing that. Don't use this tool for other purposes than just logging. We didn't want to build it for any batching or historical analysis, so analytics was not going to be supported. And we didn't want to enforce anything. Like it was up to the application developers to use it the way they want it. This is the evaluation metric we used. We had 5 criteria. Of course, topmost was cost. We wanted the total cost of ownership, be it OpEx, CapEx, maintenance overhead, to be as minimum as possible. At our scale, performance mattered a lot, so our ingestion rate was quite high. So we wanted to support our current ingestion rate. We wanted to make sure the current query latency was minimum, and we wanted to make sure the solution, whichever we arrive at, is scalable. Our engineers were already used to Grafana because our in-house metrics tool uses Grafana. So we wanted to build something which is at least on par with it. So that's why UX was one of the criteria. We wanted to make sure whatever logging solution we choose integrates with other tools. But we have been operating in this space for a while, and we have seen value of correlation. So we wanted to make sure there was integration possibility. And the last but not the least, security. Like we wanted to have data protection. We wanted to make sure in case if PII data is leaked, or if sensitive data is leaked, we have the ability to redact it. We have the ability to protect it. So the best option at that, not best option, the easiest option to do at that time was just do nothing, maintain whatever we had been doing, right? Continue existing SSH-based log analysis. No additional investment, right? But of course, it was manual, non-scalable, and it was very poor user experience. So of course, we set out and we evaluated a bunch of services. I've tried to cram everything here. I'll just go row by row. The first solution we examined was externally managed SaaS. Here, everything will be fully managed by third-party service. Pros were, we'll pretty much have no overhead of managing it in-house. But of course, cons were very high cost, potential security risk because we are sending everything to a third-party company. So that's why we rejected it, like both for cost and security concern. The other option was managed cloud logging. So we looked at a bunch of managed search and logging on a cloud framework. The pros were these technologies are mature, they are scalable, But at our scale, the cost was still significantly higher. For some cases, the UX was not that great. So eventually, this was rejected, primarily for these two reasons. The third thing was we could have self-hosted some of these enterprise-grade solutions, right? They provide very rich feature set. They have very good vendor support. But then, again, it came down to pricing. The licensing was going to be very expensive for us. And we will still be maintaining our own infrastructure, which means we will still have a team managing it. So that's why, for these two reasons, we rejected it. The fourth one was the favorite among engineers. We wanted to build our own logging solution. Yay, who doesn't want? But then that did not make sense, because that is not Dropbox's core competency. Open source and other companies are doing fantastic job. Why not just leverage them? So that's why we rejected that as well. So here comes our final choice, Loki. It is open source, so the total cost of ownership is very low. It is optimized for high-scale log ingestion, so it was perfect for our use case. The querying, the read path is equally performant with Grafana, with Loki. I'm sorry. It has native Grafana support because it was built by Grafana. So it was able to integrate with our other tools as well. And the architecture is pretty scalable. Like, you can scale individual components separately. There is good failure mode. If things fail, there are other ways to recover. So that's why we chose Loki. So what is Loki? It's open source software released under Apache 2.0 license, which means it is free to use, and they encourage community contribution. It is built to scale. It is built to scale across multiple nodes, and it is designed with high availability in mind, so it remains resilient even if individual component fails. Loki supports multi-tenancy by default, meaning it can isolate logs for each team or each category of users. It is Prometheus inspired. Pretty much, it is it is Prometheus for logging. At the core of it, Loki is a log aggregation system, which scales very well, which scales and secures your logs pretty efficiently. Let's look at a high-level architecture of Loki. Like Prometheus, each node gets an agent. In this case, it is called Promptail. It sits on each node. It collects logs. But unlike Prometheus, which is a pull model, Loki pushes, the Promptail node pushes the logs to Loki. Why it does so, you would ask? Primarily because the way logs are generated, the amount of logs which are generated compared to metrics is quite different. At such high scale, the push model works better. Once the logs are ingested in Loki, Loki takes care of indexing it, and then it exposes two ways of querying it. Either you can use Grafana, or it also provides log CLI if you're a CLI person. And that's it. At high level, this is the simple architecture. One significant difference Loki has with other logging solutions is its ability to manage the cost down. And it does that by not indexing entirety of the log. Loki only indexes your metadata. Because of that, the size of metadata is less. The range of space where it has to look for a log is less, and that's how it is able to. That is how it is able to scale. The Loki logs are grouped as into streams, and these streams are what are indexed. So let's look at an example Loki log. Actually, it is any log. Loki breaks down a log into three components: timestamp, which is the time at which the log was generated, down to nanosecond. And the second part is the key value pair. It's Prometheus-inspired key value pair. And the third part is the content. As I told you, the key value part is the metadata, which gets indexed. Remaining everything, content, is not indexed, and it is stored separately. A log stream is a stream of log entries with exact same label set. So in this case, let's say you have two applications running on two different nodes. The stream from one node, example node 1, will be all collected together because the label set is same. Service equals dummy node, and node ID equals example node 1. All of these will form one log stream, whereas logs being generated by second node, example node 2, is your second log stream here. Now let's talk about how Loki stores logs efficiently. Logs in Loki are grouped into chunks. Each log stream is stored in a separate chunk, and these chunks are sorted in timestamp order. A chunk continues collecting logs until it reaches either a target size or a timeout occurs. Once a chunk is full, Loki will compress it and flush it to an object store. The object store could be anything. It could be S3, that is what we started using. It could be Google Cloud as your blobs, or it could be your own homegrown object store, or even file system. As long as it has the interface, it doesn't matter where you are storing it. So how do we retrieve Loki logs? How does it retrieve logs efficiently? When a query comes, like in this example, let's say this one, dummy service, node ID 1, it will first try to figure out where that chunk is stored. In this case, the top query is in the top chunk, and the second one is the second one. So Loki, instead of looking through all of the chunks, it will just try to hash this query, figure out where the chunk is stored, and just look through those chunks. So in this example, let's say if you are just looking for a dummy service, you're not specifying which node you wanted, and you're specifying a timestamp from T5 to T7. So in this case, Loki knows that the label service is stored in these two chunks, so it will start going through chunks 1 and 2. It will start looking for timestamp range as per the query, and figure out which all chunks it needs to pull out. Now, one thing to note here is the timestamp in both the chunks are different. The first one has T1 to 5 as first chunk. Second one has T1 to 3. The reason for that is different nodes can produce logs at different rate. And depending on when a particular bucket is full, that is what is getting stored in the chunk. So in this case, Loki looks for first and second chunks in the first one, and second and third chunk in the second one, and combines them together, filters out the timestamp which was not needed, and it will return back the result to Grafana. Now, one thing to note here is, in this case, since node ID had two different values, we have two chunks. If node ID had multiple such values, we'll have multiple chunks. Basically, what I'm talking about is cardinality, right? In this case, service has only one value, and node ID has two values. So 1 into 2, we have two streams. But if we had multiple such values, it just multiplies. Like, for example, the last point, let's say you are using log level as one of your keys, and it has 4 different values. Status has 3 values, and path has 3 values. That means 4 into 3 into 3 is 36 unique streams. So when you are defining these key value pairs, it is very important that you pay close attention to it, because this is what drives your query performance. So just be mindful of label selection. Avoid high cardinality like trace ID, user ID, or status. The other side would be use cluster, app, or file name as your keys. So with that brief introduction about Loki, let's talk about what we have done at Dropbox. This diagram gives a high-level architecture of how Loki operates. On top, we have the yellow boxes with write and read paths. In the bottom, the green one is the object store. Right side, blue one is the shared service like Memcache used by everyone. And bottom is cluster-wide things like compactor and a distributed key value store. So when a log comes to distributor, it keeps accepting logs till it fills till a target size is reached. From there, it starts hashing those logs and tries to figure out where the ingester is located. This information, this membership, is stored in hash ring, which is typically stored in etcd. So once it identifies which ingester this log has to go to, it writes to ingester. Similarly, at ingester, you keep ingesting logs till it reaches a sufficient value. From there, you compress it and store it in your object store. Compactor works behind the scene. It keeps an eye on logs which can be merged together. And frequently, it will just look for logs which can be merged together, merge it, compress it, and store it in the object store. On the read path, when a query comes to query frontend, it divides it into separate subqueries, gives it to querier. Querier will look into in-memory cache for recent logs or object store for older logs, and then it will combine those results and send it back to Grafana. For a sense of the scale of our Loki deployment, here are some top-level metric. We are processing 10 GB of logs per second. Our 30 days of logs is equaling around 10 petabyte of data stored in our object store. Right now, we are supporting 30 days of log retention. We have close to 1,000 tenants, and our read query is very like less than one query per second. That's why most of the things we have done is on the ingestion side, not so much on the read path. With Dropbox being a storage company, one thing we did is use our internal object store as a drop-in replacement for S3. This significantly lowered our cost. Not only because it reduced our cost, we were able to increase the retention. Now we have gone to 4 weeks. Our object store is built on top of Magic Pocket. If you don't know about Magic Pocket, it's our exabyte scale key value storage system. This is where your files are stored. So we have built our object store on top of it. Magic Pocket is optimized for 4 megabyte block. So our object store works very well for small object. And that's where we saw that in comparison to S3, not only we were storing our files at a cheaper price, but I'm sorry, I got distracted. We were not only storing it at cheaper cost, but our performance was also better for smaller objects. For larger object, we are still using S3. And since object store is in our hand, we are able to reserve capacity for it. We are able to add emergency capacity to it. So it has worked out very well for us. Loki supports multi-tenancy by default. What that means for us is, for us, tenant is service. And it works very well for our existing model, because earlier, service owners will have SSH access to a particular host. Now they have access to, same access is transferred to Loki logs. There are some services which produce ton of logs, so we have divided them by project, and the ownership is at project level. As I said previously, auth was based on SSH access. Now it is on log viewing. One thing we did here was we wrote our own custom query auth proxy. Because of this, we are avoiding Grafana's complex RBAC model. And also, in order to use Grafana's model, we would have to get Grafana Enterprise. So we were able to avoid that as well. Now, one interesting thing here is how do teams share their logs? Let's say team A wants to share their logs with team B. Our way is permission is owned by team A. Team B will request it. Team A will authorize it, and we'll roll it out. It works very well for most cases, except when you are in SEV. During that time, even this small delay is expensive. So that's why we have introduced a concept called break glass. It basically allows any user with a justified reason to get access to any services log. Of course, it is heavily audited. We have a lot of safeguards in place to make sure unauthorized access doesn't happen. We run Loki in multiple data center. At Dropbox, we call it multi-homing. We use same object store in both regions, and we read out the request based on DNS. I mean, standard stuff. OK, by default, Loki has this concept of wall, write-ahead log. And it is used to recover logs when ingester exits before flushing it. At Dropbox, we disabled it because we wanted to prioritize availability over durability. In order to avoid noisy neighbor problem, we have added, I think Loki supports it by default. We have added per tenant rate limits. But these are all configurables. If a team reaches out to us, if they are alerted by a page, this can be modified, and we roll it out, the changes. One important thing is hash ring. Loki uses hash ring to track which ingester is ingesting which part of the chunk. The way it works is ingester will keep announcing, hey, I own this hash ring. And periodically, they will also announce that, hey, I'm alive, so this is my heartbeat. And typically, this is stored in a distributed key value store. We were using etcd for it, so something like this. etcd is widely used for coordination and configuration systems. It is very widely used at Dropbox, so it was our choice as well. But something we faced with it was a write contention. Since these updates are sent so frequently, and etcd was storing this entire information as one giant binary blob, and this blob would be updated using read plus compare and swap operation. This was giving us a lot of issues. With just replication factor of 3 and 67 ingesters, we were looking at 201 total ingesters. So because of this, our deployment was slow. During deployment, there will be availability alerts because of which deployment will be paused or we'll have to roll it back. And etcd was turning out to be a single point of failure for us. Luckily, Grafana made member list as the default distributed key value store for Loki. Member list is a key-to-key, peer-to-peer gossip protocol, so there is no centralized entity. And also, the updates are sent in Delta instead of entire blob being replaced. But the drawback here is it is eventually consistent. So that means our deployments are still sequential. Our deployments are still sequential, but that means the pros heavily outweighed the cons, so we are pretty happy with it. In fact, for the past 1.5 years, we have not faced any issues, and we have been able to double the number of ingesters we have. One last slide. The log indexes are determine your query plan. They determine how many log chunks has to be fetched. Previously, we were using BoltDB, but recently Grafana introduced TSDB, which is like Prometheus's database, and it is more suited for key value type of objects. So this has massively helped us with our query performance. With that, the summary of what I have been talking, our goal was to scale and enhance observability at Dropbox. We wanted to eliminate manual SSH analysis of the logs. Our approach basically was evaluating all the solutions, and we came to the conclusion that Loki was the most cost-effective and high-performance logging solution. And now, the entire observability experience at Dropbox has improved. We have improved retention. We have reduced costs, and we have a multi-tenant logging solution in place right now. So that is all I have. Thank you.